Hi, I'm Emmeline Clarkston. I am the team lead for Group 1. Our project is Anvis. It stands for Automotive Night Vision Imaging System. The other members of my group are Julian Ortiz, Carol Pearson, and Rudy Valentine. Our motivation for this project stems from our own experience as drivers and was developed through the research that we did as a team while brainstorming. Studies from both the National Highway Traffic Safety Administration and the National Center for Biotechnology show that there's a significant increase in danger to both drivers and pedestrians when driving at night. So we came to the conclusion that something must be done. As a solution to this problem, we propose an installable system that uses three heads-up displays to get a full 360-degree view around the car. The primary HUD will capture the front view of the car in infrared and display it on the windshield so that it creates an infrared overlay of the road ahead. The two secondary HUDs are used to display the side views, rear view, and diagnostics of the car to the right and left of the primary HUD on the windshield. This allows the driver to keep their focus on the road ahead. The feed from all of the cameras will be saved into the memory of the device in case needed by the user, law enforcement agencies, or for insurance purposes. To add to this, the system will be hands-free and will be controlled by voice activation. Our goals and objectives for this project is to have three functioning heads-up displays as discussed previously, and to have the entire system controlled by voice activation. This includes changing the settings such as brightness on the three heads-up displays, and to be able to switch between views on the side cameras, back camera, and the OBD information. The specifications for our project can be seen in this table. The three that we plan on demoing are the power consumption that will be less than 25 watts, the operating conditions will be in low light, and that the projection size will be at least 13 inches. This is the block diagram for our system. It is color-coded by which task is assigned to which member. The tasks with two colors are assigned to two members, where the primary member is in the center and the border color is the secondary member.
Hey everyone, my name is Carol Pearson. I am an electrical engineer and I designed the hardware, including the power supply and choosing the cameras that we used. The power supply requirements include a 5-volt rail for the Jetson Nano, the Luma projector, the IR sensor, and the right and left cameras, as well as a 12-volt rail for the backup camera. Our total power stays below our requirement of 25 watts. The car battery outputs roughly 12 volts and can be accessed through the fuse box of the car. Here you see the physical wiring design of the system. It starts with the car battery up at the top. The car battery outputs roughly 12.4 volts. We'll take it from the front of the car through the fuse box to the general area of the car, and the fuse box will go to two places, the PCB and the backup light. The backup light is directly connected to the backup camera that we found, and the PCB converts 12.4 volts to 5 volts and powers both the Jetson Nano and the projector. The Jetson Nano in turn powers the front IR sensor and the right and left cameras. This is the PCB schematic. A TI part, the TPS 56528, was used, as well as the WebEnch Power Designer to design the schematic. Input and output holes were created to allow us to solder on connections to the input power and the two loads. This layout was designed in Eagle. 4 mounting holes are used on the outside of the device to pin it to its mount device, which was designed by Emmeline. We've made significant progress with our PCB in the first few weeks of Senior Design 2. We've already finished designing and ordering it through JLC PCB, and we are currently in the testing and debugging phase of the part. The next part of the hardware design process included choosing what cameras we wanted to use for each 4 parts of the car: the front, the 2 sides, and the back. We did a field of view analysis based on the distance we wanted to be able to see to and the width of the image we wanted to be able to see. We came up with the following requirements. The front camera needs 60 degrees field of view. The 2 side cameras both need 75 degrees field of view, and the backup camera requires 135 degrees field of view. When choosing an infrared sensor for the front of our car, we had specifications that we needed to look over first. First, we needed to check that the field of view was concurrent with our previously established requirement, 60 degrees. So as you can see from this diagram, sensor 1 and sensor 4 both have that field of view. The next thing we needed to look at was resolution of the image. Since the image is going to be displayed on the entire dashboard of our car, we need to have a good enough resolution to be able to see well and have the image not be terribly pixelated. However, that comes into a problem when we are choosing our frame rate for our camera. Frame rate and resolution are inversely proportional, which means that if you increase frame rate, your resolution then decreases. But we still need a fast enough frame rate to be able to capture images at about 45 to 60 miles per hour. Therefore, we ended up paying a little bit more for our sensor than we would have liked for this reason. We ended up going with sensor 1, which has a frame rate of 60 frames per second, which is established as being good for action shots, as well as having a very high resolution of 1920 times 1080 pixels. For our two side cameras, we were able to find a Jetson Nano kit that included both side cameras and LCD screens that were both compatible with the Jetson Nano and used Jetson Nano power to operate. We still needed to check, however, that the correct field of view and a high enough resolution was used. So from this diagram, you can see that our field of view was high enough at 77 degrees, and our resolution is also very high. The backup camera had much different specifications than both the front and side cameras. First of all, the frame rate was much slower because when backing up, you go a lot slower than when you're driving forwards. So it only needs a frame rate of 25 frames per second. It also has a higher voltage rating because it connects directly into the backup headlight, which we did because it's so far away from everything else, and that makes it a lot easier to connect to the power rail. It also has the correct field of view at 135 degrees as established previously.
Hi, it's Emlyn again. So my background is in optical engineering and in computer science. And my task for the project was to create the HUD implementation and all the housing designs. There are three HUDs in our design, the primary HUD and the two secondary HUDs. The primary HUD will show the outline of the road ahead, which will come from the IR camera, which is facing forward. The two secondary HUDs, which will be placed on the right and left of the primary HUD, will show the side camera view, the rear-facing view, or the diagnostic information. This will depend on what the user wishes to see at the time. The implementation of the three HUDs will be as seen in the figure. The primary HUD will begin with the projector, which will be mounted to the roof. Then the image will be projected through the two lenses and onto the viewing screen. There it is reflected up onto the windshield. The two secondary HUDs will be placed to the right and left of the primary's viewing screen, where the images can be reflected up onto the windshield. The implementation of the three HUDs is designed such that none of them will obstruct the driver's line of sight. The final image of the primary HUD needs to have a display size of 13 inches and a projection distance of 50 centimeters. The projector on its own cannot accommodate for this specification, so we added two negative meniscus lenses to the system. The first lens will be placed 12 centimeters in front of the projector's output, and the second lens will be placed 13 centimeters after the projection's output. The lenses are placed close enough to the projector so that they do not obstruct the driver's line of sight, yet far enough away so that they can get the maximum output magnification of the image. The meniscus lens is a specially designed lens where both of the surfaces of the lens are curved in the same direction. This allows the lens to have a fairly consistent thickness around the entire lens, from the center to the edge. This prevents the light at different wavelengths from being severely separated, thus decreasing the amount of spherical aberrations seen in the final image. The reason we chose a negative lens instead of a positive lens is because the projector is within the effective focal length region of the lens system. Thus, using a positive lens would decrease the magnification instead of increasing the magnification of the final image. The reflection of the HUD causes two images to be formed on the windshield. The first image is brighter and is reflected off the first surface of the windshield. The second image is reflected off the back surface of the windshield and is dimmer. This is referred to as the ghost image. The ghost image causes the output image to be seen as an indistinguishable set of images. There are multiple ways to reduce the ghost image. This can be done optically or through image processing. In the optical domain, the first way to reduce the ghost image is by adjusting the input angle of the reflected image. The second way is to add blur to the system by modifying the lens design so that the windshield will refocus the output image. The third way would be add a thin prism to the surface of the windshield so that the angle of the ray that transmits through the windshield will be corrected so that it will exit at the same point where it entered the windshield. In the image processing domain, the ghost image can be reduced by pre-shifting the pixels of the input image so that when they are transmitted through the windshield, they are corrected. We are still in the process of testing these theories for the optimal solution or combination of solutions for our system's design. My other task in the project was to create the equipment housing and mount designs for each of the components in our system. Each component has a uniquely designed case that is set to match its dimensions and accommodate for its needs. The projector and cameras also have mounts associated with them. The projector and IR camera have fixed mounts that are angled specifically to the optical design. And the color camera has a rotational mount that the user can rotate to set to its preference to get their desired side angle. All of the cases, mounts, and racks are designed to prevent the components from getting damaged by ESD or by sudden movements of the car.
Hello, my name is Julian Ortiz. I am the third member of Group 1. My background is in electrical and computer engineering, and I've been tasked on working on image processing as well as microcontroller integration. The goals and requirements that I've been working on have been to develop an algorithm that will help enhance the information taken from one of our sensors, in this case the IR sensor, and make it easier to see for the user. Another algorithm needed deals with saving images coming from other cameras onto an SD card for future use. I've also required that the microcontroller should have everything connected to it just to make things a little bit easier for the user. Some of my choices are the following. I've chosen the Jetson Nano to be the main powerhouse for our project. It has all the required specifications we need, such as a 1.4 GHz processor as well as 4 GB of DDR4 RAM, which is good enough for what we need it for. On the algorithm side of things, I've chosen to go with Python, since it has many different libraries that deal with image processing, which will help us with what we need to do. Now we could talk a little bit about the Jetson Nano. The Jetson Nano will be running Linux as its operating system. On the Jetson Nano, we have a couple different connections to it. Two connections are going to be two cameras that are connected through CSI. Another connection will be two LCDs that are connected through HDMI. Our main sensor is connected through USB and will be displayed using a projector. Now we move on to algorithm design. I've developed an algorithm that takes a regular image given by the IR sensor, and it could be manipulated by certain parameters. These parameters are both contrast and brightness. From the picture to your right, on the top area, you could see that the brightness is being changed. And on the bottom, you can see that the contrast is being changed. When beta, which is the brightness in this case, is changed, you can see everything lights up a bit more. And when alpha is changed, which is the contrast, you can see that doesn't really help the image as much. Now let's talk about my current progress. I finished the algorithm for brightness and contrast, and it's fully functioning. I have also installed Linux onto a Jetson Nano, as well as all the programs that will run simultaneously on it. All the cameras and sensors that are needed for the project have been purchased at this time. Now let's talk about some upcoming goals I need to complete. I need to develop an algorithm that takes the images coming from the side cameras that are being displayed on the LCD screens and are saved onto an SD card for future uses. These uses can be depending on what the user needs. I also need to do some testing with the Jetson Nano when it has everything connected to it, just to make sure it runs properly, doesn't get too hot, and everything works as it's supposed to work.
Hi, my name is Rudy Valentin. My major is electrical engineering, and so far I've been tasked with doing voice recognition for our project.
So to give you some background about speech to text recognition, I'm going to tell you about the structure of speech, the recognition process, and the recognition models used in the recognition process. So phones and CNONs are the basic fundamental unit of audio and speech, and the recognizer uses these to quantize an audio waveform. During the recognition process, it splits up an audio waveform into different utterances, which are chunks of audio split up between pauses and silences. And it takes these utterances, it breaks it down, and then it puts it into a feature vector. A feature vector is just a vector that contains numerical and mathematical information about each utterance. Once it does that, it takes the feature vectors through the recognition models, which pair the feature vectors to words in a database according to the most similar feature vector. The first model is used as a language model. What this says is it restricts a word search and it increases the prediction accuracy. So basically, it'll take the previously recorded words and it'll try to predict what you're about to say next. And it does that, it takes the words with the highest probability and it creates a list for the recognizer to try to predict what you're about to say. This helps with the computation time a lot because instead of the recognizer having to sift through an entire database of words, it only has to sift through a shorter list. This is important for our project because we're trying to achieve real-time response, so we need to try to save as much computation time as we can. Next is the phonetic dictionary. This maps words to phones and contains information about pronunciation of words. Some words have many different pronunciations based on different contexts or just different speakers with different accents. The phonetic dictionary helps to maintain accuracy across multiple different pronunciations, which is important for a system that's meant to be used by multiple different people. Next is the acoustic model. The acoustic model contains acoustic properties of words and information about words will sound like. So when the recognizer receives an audio wave, it'll take the audio wave through the database of the acoustic model and it'll try to match the audio wave to the word with the most similar audio wave from the database. What I've been doing for the project so far is creating these different models. So I created a list of words and phrases that we want to use in our system, and I was able to create a language model and a phonetic dictionary. The acoustic model is a little bit more complicated to create from scratch. So what I did was I took an already existing one and I've been adapting it to work better with the words that we're using in our system. I've been doing this by recording phrases with my own voice, and then I give the software a text representation of the same phrase, basically teaching the acoustic model what sounds go to which words. Going forward in the project, we want to use the speech to text recognition to implement voice commands into our system and allow the driver to be able to control the system settings without having to press any buttons or take their eyes off the road. They'll be able to just use their own voice, which will increase the safety in the driving environment.
Hello again. I'm going to go over a little bit about administrative content for our project. We try to distribute the work evenly throughout all members, focusing on each member's strong side. This chart shown will show you how work was distributed between us four members. Now let's talk a little bit about budget. When dealing with our budget, we had to keep in mind that we weren't being sponsored. This meant we had to be a bit more cost oriented than we wanted to when selecting parts. You can see from this chart that the main area of cost had to deal with what was connected to the Jetson Nano as well as the Jetson Nano itself. Now let's talk about group progress. Our group progress is actually very good. We finished all our research as well as part acquisition. Our design is close to being done. The prototype construction and testing is where we've been lacking as a group. But luckily, having all our parts and knowing what we have to do is going to facilitate making everything come together properly. I want to thank everybody for listening. Does anybody have questions at this time?